Now we want to analyze the, method we described before. Let's start with the result. So we want to show that with this method works if we choose a rate smaller than the minimum over the chosen artificial channels from x to x hat under the condition that the expected value of the distortion is smaller than d of the mutual information of x and x hat. You see what in our method, when we create our codebook, we just need the artificial channel. Now we want to see how we get this equation here. Already before we saw that we create this codebook here. So we choose a channel. With this channel, we calculate the marginal distribution, px hat, and with this, we create this codebook here, and we create an extra word if the x hat n is not typical with xn. We will see why we need this later. Now to analyze this, the idea is that we consider the error event that x hat n of w is not jointly typical with xn, x to the n. Of course, if it's typical, then we know that these two sequences are very near together because of this definition. And if they are not near together, we will show that this is very seldom. So the idea is when we now want to show that this expectation is smaller than d. For this, we use now the theorem on total expectation and our error event E. That means we can write this as the probability of E times the expected value of the distortion under the condition of E plus the probability under E to the C times the expectation of the distortion under the condition of the complement of E. E to the C means the complement, of course, of E. So the probability of E plus the probability of the complement is 1, so we can apply the theorem of total expectation. Now the idea is that we estimate all these four things. So we will see, we will estimate the probability of this error event, and we will see that this depends on the rate. We have to choose the rate in such a way that this goes to 0. This event here, therefore, we create this extra sequence because the rule is if xn and x hat n are not jointly typical, then we use this extra sequence, which has the maximal distance to xn. So we get here d max. So we get here at the end something which you will see, we'll choose the rate that this goes to 0 and such that this is equal to d max. So we know that this goes to 0 if n goes to infinity. Then we have to show that this goes to the expected value of the distortion. And we will see that this goes to 1. Let's start with the probability of the error event. Here again, we use now the theorem of total expectation. We sum over all xn and take the probability of xn times the probability of the error event under the condition that xn is equal xn. Then we split the sum into two sums. The first part of the sum we sum over all xn, which are not typical, and the second part of the sum we sum over all xn, which are typical. If we sum, the first part of the sum can be estimated by this probability here. And we know that this probability by our theorem or the properties we have of typical sequences can be estimated by delta epsilon 1 px and n of n. And we know that this goes to 0 if n goes to infinity. So with this part, everything is fine. So we have to look at the second part of the sum. If you look at the second part of the sum, we saw that the condition xn is equal xn can be removed because x hat n is statistically independent of xn for all w. Moreover, all 2nr events in the intersections are independent. Just think how we generate the code book. We just independently choose every symbol. For this reason, we can remove this, and every event here is independent. That means we can write this. Now we write this as a contrary event. So this we can write as 1 minus the probability xn and x hat n are in the set of typical sets, like 2 to the nr. Now, this we can estimate now. Because of here only question mark, it depends how, if we use the entropy typical sequences or letter typical sequences, both will work, but for both we know that we can estimate them by 2 to the minus n, the mutual information x and x hat plus 2 epsilon times the entropy of x hat. So let's use the theorem for the letter typical sequences. Then we can estimate this in this way, and we get here this delta epsilon 1 epsilon of epsilon n and this part here. Now we know, if you look here at this part here, now we can use here from this step to this step the special property that 1 minus x is smaller equal of e minus x. That's often used this part. It just means if you look at this line, forget about this m here, just at the line 1 minus x, and as at the exponential function, then this is exactly a tangent to it, and it just hits this. And now you take it to the m, and then we have here 1 minus x to the m lesser equal e minus m times x. I will write this in more details after this proof on the board. So if you apply this, then we can write this part here in this way. And now we look at this. So we want to have that this goes to 0. Therefore, because we have here minus, this must be positive. And what must be happen that this is positive? So the rate here must be bigger than this part here, because otherwise it's negative and this doesn't go to 0. So we have to choose this greater than the mutual information of x and x hat plus 2 times epsilon times the entropy of x hat. And here you see exactly this is part of the formula, because epsilon can be chosen arbitrarily small, so this you can remove, and then we remain with this mutual information between x and x hat. So here everything is fine, because we can choose our rate in this way. That means what we have done is we have estimated this part here. Here we know already this we can estimate by d max, and this goes to 0. Now we have to look at this part here. Okay, so that's what I told you already, that we can estimate this part here by d max. That's because of how we encode. And now we have to look at the other part of this. So we have to look at the expected value of dxn under the condition of the error of the complement of the error event. We know that this error event happens with probability 1. It goes to 1 because the other goes to 0. So we know that this then goes to 1. So we only have to estimate this expected value here. what we know, if xn, x hat of n is jointly typical, then we can write, let's write the distortion measure here. We just consider this per letter distortion measure, so we can write this in this way. Now we do it for letter typical, then we can write it here in this way, so we can replace this just by, we can write here NAB of xn and x hat n of w, DAB, then we get the same like here. And now we apply the letter typicality, that the sequences are jointly letter typical. We just insert the definition here, then we get this. But if we look at this is nothing more than the expectation of dx x hat times 1 plus epsilon here. We just put this out, write it in the front, and then we get exactly the expectation. And so we have what we want. So we combine these results, and we can estimate this expectation here. By this is delta epsilon 1 of m, because that was the first part of the sum of the first estimate of the probability of the error event, as you remember. Then plus the second thing, this depends on the rate, which we have to choose big enough that this goes to 0, times d max, that's because of our coding books, plus, and now this is the other estimation, because we know that the probability of the complement of E goes to 1 if the other probability goes to 0. And this part we have just shown is equal to the expectation between the distortion measure of x and x hat times 1 plus epsilon. That means if we choose now epsilon small and n large and R satisfying this formula here, this one, then we can choose any artificial channel such that the expected value is of the distortion between x and x hat is smaller than d, and we assume that this is possible. Then we know that a random code achieves such a rate. That was the formula I present you at the beginning of the proof. The rate is bigger than the minimum overall artificial channel with the condition that the expected value of the rate distortion is smaller than d of the mutual information of x and x hat. So, and this is true as long as the constraint that the expected value of the distortion measure of x and x hat smaller than d can be satisfied by some artificial channel.